Let's take a look at projectile motion problems. Now, a key thing here is we still have cake formulas. The projectile motion, we're dealing with an object that is shot into the air, and the only force acting on it once it's in the air is the force due to gravity. We're not worrying about how it gets launched. What we care about is once it is launched. So at that point, the only force acting on it is the force due to gravity, or weight. Because the force is constant, acceleration is constant. And because acceleration is constant, we can use the cake formulas. So we have Vf equals Vi plus At. I have Vf squared equals Vi squared plus 2A dot delta S. Delta S is equal to Vit plus 1/2 At squared. Delta S is equal to Vi plus Vf over 2 times time. So with the four major cake formulas, if I have an object that is launched at some speed v and some angle theta, well, the initial velocity in polar form would be v theta. In rectangular form, if we establish our coordinate system like this, I and j, we have v cosine theta I hat plus v sine theta j hat. If you've forgotten your trig a little bit there, we have a right triangle. Hypotenuse is v, this angle is theta, so the opposite side is v sine theta, the adjacent side v cosine theta. So if this is shot some distance r here, and we're just going to take this one specific case, it doesn't necessarily have to land at the same height from which it is shot. And so I have r I hat equals v cosine theta I hat plus v sine theta j hat times time. I'm plugging into this formula right here. Plus 1/2 my acceleration. Well, the acceleration is downwards. It is negative g j hat, because I said up was positive, times time squared. So I have this formula. This is going about it the long way. I'm going to show a shortcut in just a second. So I have r I hat plus 0 j hat, which is understood. And then I'm going to go ahead and distribute the t here. So I have v cosine theta I hat times time plus v sine theta j hat minus 1/2 g t squared j hat. So notice I have this equation here with I have I hat and j hat components to it. So I have an I hat here, I have an I hat here, and then the rest are j hats. Well, I hat and j hat are perpendicular to each other. They're not mixing. There's nothing in this problem, the way I've set it up, no air resistance. There's nothing in this problem that is going to cause a relationship between I and j other than time. It's going to be in the air horizontally as long as it is vertically. And so I can separate this. I can have basically those have to equal each other. Let's not forget the time in there. And these have to equal each other. So I have r I hat must equal v cosine theta time I hat, and 0 j hat must equal v sine theta, I lost time, times time, cosine sine theta time j hat minus 1/2 gt squared j hat. Well, since I have I hat on both sides at this point, then I can just simplify this into r equals v cosine theta. And on this one, 0 is equal to v sine theta times time minus 1/2 gt squared. What I've done is I've broken it up into two different problems. I've broken it up into a horizontal problem and a vertical problem. And that is the trick for doing projectile motion problems. So let's go through an example. I have an object being shot off of a cliff at some speed of 25 meters per second and an angle of 30 degrees. I want to know how far from the base will this land. Some distance r. It starts out at some initial height of, we'll make it 20 meters. And so what I'm going to do is I'm going to write down the major components here. So we have delta S, Vi, Vf, A, and T. I have a horizontal set of information and I have a vertical set of information. Do not mix them. The only place except for time. Time is the one thing that is going to guarantee to be the same for both. Well, horizontally, it's going to go some distance r. Oh, let's establish a coordinate system. I hat, j hat. So in essence, my horizontal is my I hat, and this is my j hat. Vertically, it's going to go from here down to here. It starts at this elevation and ends at this elevation. So this is negative 20 meters. My initial velocity, this will be 25 meters per second times the cosine of 30 degrees. And this is 25 meters per second times the sine of 30 degrees. Final's not given. It's easy enough to know what that's going to be, but final we don't officially know at this point in the problem. Acceleration horizontally is 0 meters per second squared, and here it's negative. Let's make this Earth. 9.8 meters per second squared. So this is what we're starting with. We can work through the math on this. 12.5 meters per second, and this one over here, 21.65 meters per second. Because acceleration is constant vertically, I have a set of equations for that. Because acceleration is constant horizontally, I have a set of equations for that. And it's the same set of equations. It's the cake formulas. So just pull out what we had written before. And this, one of the big things you usually have to do with this is to find time. So let's go ahead and find time. Horizontally is not going to restrict what the time is. The vertical is going to restrict the time in the classic problem, because how long it's in the air depends upon how long it takes for it to hit the ground, which is a vertical thing. Horizontally, it's just going to go horizontally until it hits the ground vertically. So we're going to be using this information in order to find the time. And so I'm going to use this third equation here. So delta S is equal to VIT plus 1/2 AT squared. And negative 20 is equal to 12.5 T minus 4.9 T squared. We have a quadratic equation here. So 4.9 T squared minus 12.5 T minus 20 equals 0, getting everything over onto the left-hand side. Now I can use the quadratic formula. So my time, I should have two answers here. From another video, what we're looking at here is the math problem is solving this parabola right here, the x-intercepts of the horizontal axis. And so I should expect two times. One's negative, one's positive. The absolute value of the positive should be bigger than the absolute value of the negative. So this becomes 12.5 plus or minus the square root of technically negative 12.5 squared minus 4 times 4.9 times negative 20 divided by 2 times 4.9. So I get 12.5 plus or minus. Notice the discriminant has to be positive because, well, that's a positive number, and I got two negatives here making that positive. And so I get 23.415 divided by 9.8. I get 3.665 seconds, or negative 1.114 seconds. So this obviously is the one that has physical meaning here. And so now we bring in the horizontal. I'm going to use the exact same base formula right here. So delta S is equal to VIT plus 1/2 AT squared. My range, therefore, is 21.65 times my time, which is 3.665 plus 1/2 times 0 times time squared. So obviously, well, yes, there's a value for time, but that whole thing is going to be 0. And it just comes down to distance equals rate times time. So 21.65, 3.665, and I get 79.35 meters. That is the range. It's going to fall just over 79 meters away from the base of the cliff. Now we can change this problem around some. I'm shooting this thing at 25 meters per second at some angle theta, and it's going to land 79.35 meters away. And the question is, what is the angle? Now, obviously, it should be 30 degrees if we've done it correctly. But let's just work through this type problem. Again, this is 20 meters from here to here. I had a negative sign there because the displacement will be negative 20 meters, but it's not positive or negative, so let's get rid of that. Not positive or negative in terms of displacement until we set up a coordinate system. So let's do so. I hat, j hat. And we set up a horizontal, or I hat equations, and our vertical, or j hat equations. We got our big 5, VI, VF, A, and T. So this is 79.35 meters. This is negative 20 meters. VI is 25 cosine of theta. This is 25 sine of theta. Technically, let's squeeze a meter per second in there. This is 0 meters per second, and this is negative 9.8 meters per second squared. We can find, well, we don't know what the time is. We don't know what theta is. And so this is obviously a far more complicated problem. So if I plug into the same formula as I did before, I have 79.35 is equal to 25 t cosine of theta, because it's VIT. I'm just moving the time in next to the 25, cosine of theta. And I have negative 20 is equal to 25t sine of theta minus 4.9 t squared. So we have two equations, two unknowns. This is solvable. It's not necessarily nicely solvable, but it's still solvable. How do we approach it? What I'm going to do is solve for time in this equation right here. So time is 79.35 over 25 cosine theta. Plugging into the second equation, I have negative 20 equals 25 times 79.35 over 25 cosine of theta times sine of theta minus 4.9 times 79.35 over 25 cosine of theta squared. So that gives us negative 20 equals, and I can work through some of this. Silly me. 25s cancel out. That makes life slightly simpler. So I have negative 20 equals 79.35 tan theta minus, and now let's do the constant piece of it, minus 49.36 secant theta, secant squared theta. Now, you could do it all in terms of sines and cosines, and then isolate the either sine or cosine, and then you end up with the radical, and then you square it. This is the slightly slicker way of doing it, because we do have a relationship there. I know that sine squared theta plus cosine squared theta is equal to 1. If I divide everything by cosine squared, I get tan squared theta plus 1 is equal to secant squared theta. And so since I have a secant squared theta there, I can make that substitution. Now, what I'm going to do is I'm going to let, just because I don't like writing, Q is equal to tangent of theta. So I have negative 20 is equal to 79.35 Q minus 49.36 Q squared plus 1. Distribute, negative 20 equals 79.35 Q minus 49.36 Q squared minus 49.36. I have a quadratic here, so let's get everything over on the one side. So I'll pull everything over to the left. 49.36 Q squared minus 79.35 Q plus 29.36 equals 0. And solve for Q. So Q is equal to 79.35 plus or minus the square root of 79.35 squared minus 4 times 49.36 times 29.36. That discriminant better be positive, over 2 times 49.36. 79.35 plus or minus 22.35 over 98.72. I'm going to end up, remember that Q is the tangent of theta, it's not the angle itself. So I have 1.030 or 0.57739. And that is equal to Q, or the tangent of theta. And so theta is, let's do an arctan, and I get 30.00 degrees. Should not be a shock here, but there is a second answer. Arctan, 45.85 degrees. So there are two answers to this particular problem. They will not spend the same amount of time in the air. So one is going to be more like that, and the other one is going to be more like that. So on a test, if I'd done something like that, assuming that you got that right, you'd at least be able to get one of the answers, but there is a second answer there. And so that's the essence of projectile motion problems. The rest of them, it's just a matter of what do I give you and what do I not give you, and working through it. Now, I've noticed from students in the past that a problem like this seems to really flummox them, because they start into it, and like a lot of physics problems, you start into it and you're going, am I doing it the right way? Am I about to waste an hour of time trying to solve this the wrong way? And so there's a certain amount of, I don't really like to use the words confidence, that's what I was about to say, arrogance, but a certain amount of confidence that you need that you're doing it the right way and you will come out with an answer in the end. I know, not particularly reassuring, but there it is.